This heat equation, as far as I've read about a while ago, so apologize if I'm wrong, but I think it is rising from the heat equation, and there is this Laplace operator, delta squared. The book explains nicely about the motivation behind this superscript notation, but this kind of measures the heat at the given point. And it's a two-variable function, phi, capital phi in the Greek letter. I think in that heat equation, there's a two-variable thing, and one of the variable is actually time. Okay, but anybody remember this Laplace operator, delta squared? Right, second partial derivative, one variable, right, plus the second partial derivative, and the other variable. All right, that's the Laplace operator. That's it. And heat equation is this Laplace operator set equal to 0. All right. What this one measures, as far as I know, is the in and out of the heat of a certain system. How much heat is going outside. If it is stable and the temperature is not changing, that means amount of that's going in and out, amount of energy that contributes to heat that in and out is 0. All right. Whenever you see the 0, something going in could be the number of particles, number of, whatever the vector field, and then electrons set equal to 0. That is called conservation principle. Something, the total amount of things that are going in and out is 0 is a conservation principle. All right. So setting this Laplace operator equal to 0, that's called the heat equation. It is actually describing that sort of a conservation equation there. So that's that. That's the one thing. Then we were looking at, that was the physics side. We're looking at nice complex function that is described like this, u plus iv. And what was the relation between these two things? This u and heat equation and our analytic function. And u is, well, any function that satisfies this equation. This phi is called, what was the name of this phi that satisfies this Laplacian equation? Is called harmonic, right? If this thing becomes 0, it's a harmonic function. That's the physics side. Now it's a pure complex analytic function in here, u plus iv, and then it turns out u is harmonic. Remember that part? I think in the test I returned today, many of you actually successfully showed this is harmonic function. This harmonic function. To show this is a harmonic function, what did we use? Some important equation, right? What is that equation? Cauchy-Riemann equation, right? Cauchy-Riemann equation allows you to swap that, and eventually we have used Clairaut's theorem. Is that right? To show that. How about V? V is also so is V, right? V is also harmonic function. Correct? Yeah. All right, that's good. But today what we're going to do is that all the harmonic function actually rises from the complex analytic function. So here we were just looking at some harmonic function in here. And I am saying there's a complex analytic function whose real part is your harmonic function, and the imaginary part is whatever that comes with it. So we call this imaginary part that is attached to this phi is called harmonic conjugate. Or it's just like a converse. If I have an analytic function, CR is satisfied. Now CR is satisfied and continuity is there, then we conclude analytic. Now here's a harmonic function is given, arbitrary harmonic function is given in there, and I'm saying it's actually coming from complex analytic function. So that heat equation is closely tied to the bigger picture, the complex analytic function. It's quite interesting. So I'm stating here all harmonic functions rise from where? Analytic function. And this again explains what how this complex number is closely tied to the nature of physics, I think. It's not just like some gadget we did mathematically developed to put things together, to combine e to the x and cosine x together. And this is good evidence that complex analytic function is a part of the nature, how the nature works, right? And from that kind of belief in physicists and quantum mechanics, all that, it is not something that mathematicians is invented, and they believe it's the way that actually the algebra works in the nature. All right, so here it's how we start. So for example, let u be a harmonic function. Right? And all this discussion is like a local nature. Soon when we go to a fundamental theorem of line integrals and all that, local versus global causes a little bit of obstruction. Then that obstruction is measured in the next section, integration and all that, and go into a deeper and deeper area of the mathematics. So differentiability and analytic properties are local. There's a tiny amount of a neighborhood there, and everything is okay. So every calculation we're doing here is in its local nature. So harmonic is there, and we wanted to show there exists a complex and analytic function, right? Such that, that symbol, E backwards symbol, there exists this complex analytic function such that f of z gives you that real part being that and imaginary part being that, right? So u is given, and we have to construct that v and show that it satisfied one condition? Analytic condition. What is that? How do you show something is analytic? CRE, continuous partial in CRE. So we construct this v and show it satisfies CRE, then boom, this function is analytic. Therefore, this arbitrary harmonic function u rises from complex analytic function. Okay? So here is the goal and our target. That's what we want to show. But here, if it is, what is harmonic function? It's uxx plus uyy equals 0. That's the very definition of harmonic function, right? And this one gives you following condition: uxx equals negative uyy. This is the condition we have. All right? How do you construct v if this is going to happen? The relationship between u and v is connected through Cauchy-Riemann equation, exactly CRE. So how do you go from here, this nice equation, to that? Is that first you strip off an x by integrating, then you get ux there, right? How do you go from here to there? Integrating with respect to x, right? So that integration is indefinite integral. That's what I'm thinking right now. So integration is not a good word. It's an antiderivative is a better word, right? So you look at antiderivative of ux, and it's there. Now we know this one is supposed to be negative the vx, right? And then if you no, this is supposed to be vy. I'm sorry, right? That's the Cauchy-Riemann equation. It's supposed to be vy. So you look at this guy and define this one to be vy and anti-differentiate one more time, and then it'll give you the candidate for v. And then you have to check that v that you constructed actually satisfy CRE. All this thing is actually the part of a thought process before you go into the following setup. Often math textbook doesn't explain the setup. Here it is. Here's the answer. Let this one to be that, then everything else is satisfied. But the motivation behind it is you look at this harmonic Laplacian equation and think about how to construct the v out of it, right? And once you construct it, then you show it's satisfying the CRE. So because of that motivation, we're going to look at it here. uxx negative uyy, they're the same function, right? Correct? To show before, if it is rising from harmonic function, before in there, oh yeah, if it is an analytic function, then it became harmonic. What theorem did we use? CRE and eventually Clairaut's theorem, right? It's about order of differentiation. Now we're doing this integral, to going backward. There's also a theorem called it doesn't matter if you integrate x first and y later, or y first and x later. So it seems like completely analogous to Clairaut's theorem, just the integral operator versus differential operator, right? Differential operator is called Clairaut's theorem. What about the other one? Integrating x first and y later and y first x later. It's going to be the same. Anybody know that theorem? It's called Fubini's theorem. Love Fubini's theorem. So I made a video out of it and all that. But anyway, so to strip off this x, right, I'm going to do dx first. That's the antiderivative the notation. Then later, I'm going to do dy, right? So it's going to be x in there and y later. Does that make sense? So usually in the indefinite integral, you don't put anything, but I'm going to end to definite integral. So, but it is the idea I'm writing and bit by bit and explaining the process of it. Now, we started with the ux equal to negative uy, right? That's the same function, and it doesn't matter in what direction you're integrating, right? So since this one has a y different, the derivative is there, I'm going to actually integrate y first. It doesn't matter, right? And then x later, dx. Then it's supposed to be the same. What theorem? Fubini's theorem. So it's because of the Fubini's theorem. And I hope you see the similarity between Clairaut's theorem and Fubini's theorem. Okay? Fubini's theorem, we're looking at the same function, uxx, uyy, negative uyy, doesn't matter which order you differentiate it. These are right now antiderivative. When you do antiderivative, you have choices, right? What is the antiderivative? X. 1/2 x squared plus a constant, right? If it is a two variable, remember this gets more complicated. If I'm looking at ux being x, what is u? If it is a two variable function, of course 1/2 x squared, right? But how does the constant look like this time? Something in terms of y, right? Something in terms of what, like phi of y. Then, if you differentiate with respect to x, that all disappear. And you can see this becomes a significant factor when you do iterated integral like this. So, if you sloppy and feel more comfortable about indefinite integral than definite integral, if you enter it like this and being careful like this, you end up at exactly the same amount of difficulty you're running through. So, at the beginning, it's better to define function always as a definite integral. So if you look up all the books in the calculus book, when they define actual functions, when they're actually explaining, they always use a definite integral. They never use indefinite integral. Indefinite integral is just a mere tool in the process of solving problems. And theoretically, you always have to define function in precise manner, not vague manner. Definite integral is always precise. I said this is a local calculation, right? Local calculation always start with one point, a comma b. Now we're defining this u harmonic function. We have this nice, everything is okay or just around that a point b. And we're about to define a function around it so that it's based on x equals a and y equals b and x and comma y is somewhere in the neighborhood. Then if you do the definite integral from a to x, definite integral to y to b, and it's going to be clear meaning. There's no this type of thing. Just, everything is completely determined. And because now this is a two-variable function, clearly defined two-variable function, there's no something like this, phi y, ambiguity is in there. So what this means is that I'm going to actually exaggerate over here a little bit so that I can explain to you what's going on with that integral. So suppose we have this nice neighborhood stretch around. Maybe it's actually entire complex plane, but our x comma y is there, right? Now let's think about this process. We're integrating inside with respect to x first. So that one is kind of, like this, integrating along the x-axis, then integrating along the y-axis, right? And integrating this one, integrate along the y-axis first, and integrate along the x-axis. Something like that is the meaning of this iterated integral. It's different from the double integral. All right? So this is the same function expressed in a different way and taking advantage of the Frobenius theorem. This function I'm going to call v tilde. V tilde is not quite v, so we're going to adjust it to x comma y. And you have to understand this is a clearly defined function, v tilde. Right? A and b integrated this way or that way. Frobenius theorem says you're going to end up at exactly the same number no matter what your x and y there is. All right. So now we're going to test, is this v tilde is going to satisfy, we have u and v tilde is constructed. We want this v tilde satisfy what? U and v tilde satisfy continuous, because of the antiderivative is continuous is there, the CRE is what we want. So we're going to calculate v tilde x. All right. V tilde x. V tilde x is, you see that v tilde version, we have two different versions. If you look at this version right there, x is out there, right? So differentiated with respect to x. This is called the fundamental theorem of calculus. Fundamental theorem of calculus. Here's an integral from a to b outside there. Just kind of ignore what's inside. I want you to look at the second equation as an integral from a to x dx, differentiating with respect to x. What happened? It cancels, right? And it just becomes b to y and negative uyy, where x is kept constant and y is the variable. And here's a dy. Does that make sense? I'm not using this version, I'm using this one in here. And I have nice expression. Correct? Right. So because this last one here is a y and the dy, can you further actually integrate somebody? This uyy is derivative dy in 2 times, right? So if you go back and dy, that's an antiderivative. What is an antiderivative of negative uyy with respect to y? If the last operation of derivative is y. Negative uy. Does that make sense? If you differentiate this one with respect to y, then you get uyy. And this integral is going backward u. So that's an antiderivative with respect to y. Antiderivative of negative uyy. So, and then we're plugging in what? Y and b there, right? Okay, so that's going to be negative, what do we have? Uy x, x here is a fixed, and y here is y, and minus, but there's minus, there's a plus, and uy x and b. Is that good? So we're going to do next time we want to compare, see how this, well, this is a good part. Vx is supposed to be, what is it Cauchy-Riemann equation says? Vx is supposed to be negative uy, right? Do we have a good shape right now? Vx is supposed to be negative uy. We just have this extra thing. We have to get rid of it. Then we have a Cauchy-Riemann equation. Okay? So let's do Vy. What are you going to do with the Vy? V is here. V tilde is here. We're about to differentiate with respect to y. Which version are we going to use? First one or the second one? We're about to differentiate dy. Which one is giving you a nice result? First one, dy is out there, so if you differentiate it, it cancels, right? So what happens? So ux inside stays uxxx and dx. Is that right? Yeah. So now you're actually integrating. What is an antiderivative of uxx with respect to x? It's ux, right? and we're plugging in x and a, right? So it's a ux, x, y is fixed as a constant, minus this one is going into the slot of x part, a, y there. Again, if you look at this Vy and it is Ux, that's a good part of a Cauchy-Riemann equation, right? So you have to think about getting rid of this one by adjusting it. All right, I have a V tilde that was defined like that before. So we're going to now we're really going to define V, which will have this condition. So we're going to keep that V tilde. That's going to give us, if you differentiate x with respect to x and y here, you get this term and that term coming out because I have V tilde in there, right? So I have to just linearly add two more things so that we get rid of this guy and get rid of that guy. So I forgot what the answer was, so I'm going to take a look at it here to make sure. So when you're differentiating Vx, V has to come from the Vx, so that should be minus to cancel that. You want to cancel that, it's a negative. And we're differentiating with respect to x, so I'm going to put ax there, and uy d, sorry about this, you have to keep that b in there, that's a key part, dx there. I'm adding this one by targeting this one, so if I differentiate it with respect to x, then it's just going to be uyxb in there, and then it's going to cancel that part. Right? So I want to create that one after I differentiate it with respect to x, so I integrate it here. This one needs to go. So after you differentiate it with respect to y, then you have to put some y integral in there, ux ay, and dy, keeping a is in there. That turns out to be good. So this one, b is given constant, and this is completely done as one variable function in x and one variable function in y. And if you add these two things, maybe now it's going to satisfy that condition, and that's something that you have to work out. So now I'm going to do Vx, right? So it's going to be V tilde x. And how about this one? What happened if I differentiate this one? It's a variable in x and dx in here. Therefore, it's fundamental theorem of calculus. One variable, everything here is just in x. Therefore, it's a uy x comma b, right? How about this one? I said this is actually one variable function because I replace x with a. Now I'm differentiating with respect to x, and what happens to that guy? Only in terms of y, right? With differentiated with respect to x becomes 0. Okay, so these two things that I'm adding in there to get rid of this additional factor, it's behaving nicely, it's complementing each other, not making things complicated. So what is now the Vx is a Vx tilde. We have calculated Vx tilde, which is negative uy plus uy xb, but there's negative uy xb, right? So they cancel, it gives you negative uy. So by adding that two terms in this partial, we successfully got rid of that additional term there. You can see this is a function in x, it is a function in y. They rises as you go through antiderivative process carefully when you do this two iterated integral. So let's do the Vy. So V is the formula right here. V tilde, two variable function, minus one variable function, plus another one variable function, right? So what is Vy tilde? It is Vy is a V tilde y in there. How about this one? This is a function in x, right? And we're differentiating with respect to y this time. So what happened to that guy? That becomes 0. And plus, this one is indeed in y, so fundamental theorem of calculus says this is going to be just that function with a y in it. Right? But this Vy has this negative term, so it's a ux xy minus ux ay. and plus out there ux, ay is out there. So they cancel, and that was the whole idea about the setup. So now this v, which is v tilde plus minus of this x function and y function adjustment, now gives you vx equals negative uy, vy equals ux, right? What is this equation called? Cauchy-Riemann equation, right? Cauchy-Riemann equation. We started with harmonic function u, and there is this complicated construction that only mathematicians care about. Then I showed that with a few adjustments, there is this function v, which I constructed in here. Let me go back to the beginning. We started with the harmonic function, and our goal is to construct this function v such that this u and v satisfy CRE. And there was this hard definition of this v right there. And as we just differentiated using the Fubini's theorem, taking advantage of the Fubini's theorem, we have Vx, we constructed as negative Uy, Vy as a positive Ux. That's a CRE, right? Therefore, Fu plus Iv is what? Differentiable. Differentiable, that's right. Differentiable and analytic if it is happening in the neighborhood, right? It's a neighborhood analytic. All right. Well, I think this was a really sophisticated example of advertising the fact that complex number is a part of our nature. Is that you see this thing rises naturally in pair and in complex forms. All right. So they, because of all this thing, physicists begin to take this complex algebra really seriously. It's a part of it, and the reason that quantum mechanics is stated through this complex number system is probably because of all these things. They believe this is actually what's happening in the nature. All right. So next thing, let me use the 1 minute to advertise next. This phi is a energy function, right? The heat energy function. So you know that the level curve. Did you hear about the level curve? This energy function fixed to alpha. Did you hear about those? So if you move around in here, the potential energy of a heat is all the same, right? And here's a next level of a level curve. So if you move around in here, the potential energy level of a heat energy is the same. It's called a level curve, right? So how is heat's going to flow? Heat level phi here is, let's say, is 1, and heat level there is 0.5. And if you're, how is this heat is going to flow from high to low or low to high? The high to low, right? That's how it flows. And so the heat flow, if you look at it here, express it as a vector toward to that guy. Toward to that guy. Does anybody know the exact description of the direction? We know inside there's a lower heat there, right? So the direction of the heat flow is toward to that. But what is exactly the direction? The gradient vector, right? The gradient vector. Unfortunately, gradient vector is just going higher. Remember in the physics, they use the potential function. They put negative in front of it. Remember that part? Have you taken it? That's why. Actual flow is actually high to low, but the gradient vector gives you opposite. There, the gradient vector is mounting up the mountain of the level curve. So you have to go backward for that. Putting the negative does the right thing to capture the actual flow of a vector field to the lower level. So the direction of this gradient vector, or the opposite direction of the gradient vector field, is the direction where the rate of change of this heat energy level is maximized. Remember that part from calculus 3? The gradient direction is the direction where the rate of change of this value, the heat energy, is maximized. So it's a principle. The nature will take that path to maximize the rate of change or maximally minimize the rate of change. So all the heat flow is done through this gradient vectors, right? So that geometry of this vector field is important, and that's what's coming up. Line integral vector fields, and again this thing rises from the complex function again. So that's another interesting phenomenon that is the evidence that this complex number is really part of our nature. So I'll stop here.